Assalamualaikum, we are from Group 4. In this video, we will present the simulating of a 4-bit synchronous counter and 2 to 4 decoder we enable using logic gates in Logisim.
Introduction to circuits purpose. Logic circuits are critical components of digital system that transform binary signals 0 and 1 into logical operations and decisions. These operations, such as AND or NOT, are accomplished through logic gates such as AND or NOT, NAND, NOR, XOR, and XNOR, which can be combined to form advanced circuits represented by Boolean expressions, truth table, and logic diagrams. Logic circuits are divided into two different categories, which is combinational circuits, whose output depend entirely on current inputs, and sequential circuits, which rely on both current inputs and stored outputs. They are frequently used in computer systems, such as ALU, control units, memory, and input-output devices to manage data flow, process information, and facilitate communication between the CPU and external devices. Overall, logic circuits represent the foundation of digital electronics and are essential for understanding how computers and digital devices operate. This is our logic diagram for 4-bit synchronous counter and 2 to 4 decoder we enable. In this section, I will explain the simulation design of a 4-bit synchronous counter implemented using T flip-flops and AND gates. The circuit uses 4 T flip-flops labeled Q0, Q1, Q2, and Q3, all connected to a common clock signal, which makes the counter synchronous. An enable input is provided to control whether the counter is active. When the enable is set to 1, the signal path becomes active and the connected wires turn light green in the simulation, indicating a logic high. This allows the clock pulses to trigger the flip-flops. When E equals to 0, the wires remain inactive and the counter does not change state. The flip-flop Q0 toggles on every clock pulse when E is enabled, causing its output to alternate between 0 and 1. When Q0 becomes 1, the AND gate connected to Q0 outputs a high signal, which enables Q1 to toggle on the next clock pulse. In the same way, Q2 toggles only when both Q0 and Q1 are high, and Q3 toggles only when Q0, Q1, and Q2 are all high. Each time these conditions are met, the corresponding AND gate output turns light green, showing that the toggle condition is satisfied. Reset input is used to clear the counter. When reset is activated, all flip-flops return to 0000 and the green signals disappear as the outputs go low. Overall, the simulation clearly shows the counter counting in binary from 0000 to 1111, with the green highlighted wires visually indicating when the signals are active. This confirms that the circuit works correctly as a 4-bit synchronous counter. For the truth table of the 4-bit synchronous counter, the table lists the clock count along with the corresponding outputs Q3, Q2, Q1, and Q0, which represent the binary state of the counter. At each clock pulse, the counter increments by 1, following the standard binary counting sequence. The outputs change synchronously, meaning all flip-flops update their state at the same time on the active clock edge. The counting starts from 0000 and continues in binary order up to 1111, which corresponds to decimal values from 0 to 15. Each row in the truth table shows how the output changes with each clock cycle. After reaching the maximum count of 1111, the next clock pulse causes the counter to reset back to 0000. This behavior is shown in the final row of the table, confirming the reset operation. Overall, the truth table verifies that the counter follows the correct binary sequence and operates as expected for a 4-bit synchronous counter. The next slide shows the simulation design of 2 to 4 decoder we enable. The circuit has two main inputs, which are the enable and the select input A. It also has 4 outputs labeled Y0, Y1, Y2, and Y3. The decoder converts the binary input into one hot output, where only one output is active at a time. When the enable input is set to 0, the decoder is disabled. In this condition, all output lines remain low, and no wires turn light green in the simulation. When enable is set to 1, the decoder becomes active, and the signal path turns light green, indicating a logic high. The value of input A then determines which output line is activated. If A equals to 00, output Y0 becomes high and turns light green, while Y1, Y2, and Y3 remains low. If A equals to 0, 1, output Y1 becomes high, If A equals to 1, 0, output Y2 becomes high. If A equals to 1, 1, output Y3 becomes high. At any time, only one output is active, which clearly demonstrates the decoder function. The green highlighted wire in the simulation visually shows which output is selected based on the input value. Overall, these simulations confirm that the circuit correctly functions as a 2 to 4 decoder with enable, where the enable input controls activation and the input value determines the selected output. For the truth table of the 2 to 4 decoder with enable, the table lists the inputs A1, A0 and enable, along with the corresponding outputs Y0 to Y3. When the enable input E is 0, all outputs remain at 0 regardless of the values of A1 and A0. This confirms that the decoder is inactive when it is not enabled. When E is set to 1, the outputs depend on the binary combination of A1 and A0. For input 00, output Y0 is set to 1. For input 01, output Y1 is set to 1. For input 10, output Y2 is set to 1. For input 11, output Y3 is set to 1. From the truth table, we can see that only one output is high for each valid input combination when the decoder is enabled. This matches the expected behavior of a 2 to 4 decoder with enable and confirm that the circuit operates correctly. Next, I continue with circuit functionality. For 4-bit synchronous counter, a digital circuit that counts in binary from 0000 to 1111, which is 0 to 15, it uses 4 JK flip-flops triggered by a common clock signal, ensuring all flip-flops change state simultaneously, which eliminates ripple delays seen in asynchronous counter. The least significant flip-flop, FF0, toggles on every clock pulse, while each higher order flip-flop toggles only when all lower order outputs are high, usually using AND gates. This arrangement produces a coordinated binary sequence that resets to 0000 after reaching 1111, forming a mode 16 counter. Such counters are widely used in digital clocks, timers and frequency dividers due to their speed and accuracy. While for 2 to 4 decoder we enable a combinational digital circuit that converts a 2-bit binary input into 4 distinct outputs, where only one output is active at a time. It has 2 inputs, which is A0 and A1, 4 outputs Y0 to Y3, and an enable input E that controls the operation of the decoder. When the enable signal is high, one output is asserted high based on the input combination. 00 activates Y0, 01 activates Y1, 10 activates Y2, and 11 activates Y3, while the remaining outputs stay low. When the enable signal is low, all outputs remain low regardless of the input values. The circuit is implemented using AND and NOT gates to ensure unique output selection and is commonly used in address decoding, data routing, and control logic in digital systems. Next, application in real CPU component. For 4-bit synchronous counter, it can serve as microprogram counter in a CPU's control unit, providing sequential addresses for micro instructions that carry out a single machine instruction. In comparison to asynchronous design, this technique provides stable, high speed, and exact timing for internal CPU functions. In an actual processor, each instruction is executed in several micro steps, from fetch to decode, to execute, and to write back. Next, the CPU operates on a synchronous counter to determine which micro operation should be performed next. Because all flip-flops use the same clock, the counter changes state accurately and in time with the CPU clock. 4-bit asynchronous counter also ensures that the control unit performs operations correctly. Following that, for 2 to 4 decoder with enable, it is an essential component in real CPU systems, used mostly for memory address decoding such as chip selection and register selection within the CPU's control unit. The enable pin is essential for controlling when the decoder becomes operational and enhancing its capabilities. In an actual processor, when the CPU wants to read or write to a particular memory block or register, it sends binary address bits. The decoder converts address bits, for example, 2 bits with 4 outputs into only one active line. Moreover, only the memory block or register that's selected is enabled. This also prevents conflicts and enables more accurate addressing. Next, we move on to challenges. There are 3 challenges that we face and overcome while doing the entire task. First and foremost, the enable signal is not working. For starter, let me explain the problem. When the enable signal is set to 0, some of the output is still on, which should not happen. The cause of this problem is that the enable signal is not connected to each AND gate in the circuit. Because of this, some gates continues to operate even when enable is off. To fix this issue, we must ensure that all 4 AND gates receive the enable input. This way, the enable signal properly controls the entire circuit. When the enable value is 0, all output will be 0, and when enable is 1, the circuit will function correctly. Second, output start at high or low. The problem is that some output do not change even when we change the inputs. This means the circuit is not responding correctly. The cause of this issue is faulty wires or unconnected inputs. When a gate input is not connected, Logisim does not receive a proper logic value, so the output becomes incorrect or stay constant. To fix this problem, we need to check that every gate input is properly connected. Make sure there are no loose wires or missing connections. Additionally, we can use the fault tool in Logisim to test each input and connection point. This helps us confirm whether the signal is reaching the gate correctly and ensure the circuit works as expected. And last but not least, confusion to choose the features such as the symbol and the gates. The problem is being unfamiliar with the interface and the functions of the available components in Logisim Evolution. This issue is because of lacking experience in using Logisim. To fix this problem, we have learned from YouTube tutorials, use references from others who have experience, and explore the application through practice, which help us understand the tools better. In conclusion, we selected topic 2, 4-bit synchronous counter, and topic 3, 2 to 4 decoder with enable, because both components are essential for understanding how a real CPU controls its internal operation. The 4-bit synchronous counter represents how the CPU sequences the state of the fetch, decode, execute cycle using the system clock, while the 2 to 4 decoder with enables models how the CPU selects memory or register by activating only one output line at a time. Overall, these circuits clearly demonstrate the core CPU processes of instruction sequencing and hardware selection, making them practical and easy to simulate in Logisim.
That's all from us. Thank you for watching.